Okay, so in this video, it's the test review for the, what is it, momentum? Yeah, momentum. So our first question asks, what are the rebound velocities? So what we're given is the M1 comes in at the origin, and the M2 does as well, and at these two different angles, but they're weird angles. So we have to figure out how to convert all of these correct angles into the ones that we can use like indefinitely, so they all make sense and equal in the end. So the rebound angle here comes in at 62.8 degrees here, and the angle rebound is 48.8, and for M2 it comes in and rebounds, and 71.0 is its rebound angle. So let's convert all of these angles into ones we can use. So we can do our theta initial for M1 theta. So look, basically we have to extend this line out. So this is what it'll look like. It's going to be coming in, and we extend the line past the origin, right? And now we have to find it, so it looks like that. We have to find pretty much this whole angle here. So what can we do? Well, which we can do simple geometry or math, whatever. So this is 270, this whole thing. And then the opposite angles, right? It looks like this, and then it's this. This is 62.8, so that means this would be 62.8. So 90 minus 62.8 is 27.2, and then we add 270 to that, 270 plus that, and we get our first angle as 297.2 degrees. So now our theta for the second one, initial, it's going in here. So what's this look like? Well, let's draw it again, and it's coming in and extend it, so it looks like that. This is 14.3, so that means this would be 14.3, right? And then we're trying to find this whole angle, this big angle right here. So how do we do that? Well, we know this is 180, and we can do 90 minus 14.3, 75.7, and then 180 plus 75.7, we get 255.7. 255.7. So that's kind of the general way how to do it, right? You extend the line out, whichever way it's going, right? So if it's coming in this way, it's going to be extended. So then we can do the rebound angles. So this one, it's kind of already given, 48.8. It's this way, and it's coming out this way. So we can just find this whole angle, right? So we can do 180 plus 48.8. and that's 228.8. So our theta final one equals 228.8 degrees. And our theta 2, it comes out right like this, and this is 71.0. And so we can honestly really easily just make this negative 71 because it's coming out, right? 71 regularly would look like that. Negative 71 would be flipped, right? So we can just do negative 71. Or if you want to do the longer method, you could do this, find this as 270, and then 90 minus 71, and then 270 plus 19. And it would also be 289, but they're the same thing, they're interchangeable. So yeah, that's how to find all the thetas. That's like the hardest part. And then what you can do from there is do the setup. M1v1 plus M2v2 equals, blah, blah, blah. So let's set that up. M1.455, V initial 12.6, and we're gonna do the x direction. So then we're gonna use cosine the theta we found, which was 297.2, right? And then it is going to be plus M2, which is 0.343, times V, which is 14.3, times theta, which is 255.7. Sorry, this is cosine 255.7. Then that is going to equal the m1.455, the v final, which we're trying to find, v final, and this is the v final for 1, so vf1 times cos our rebound thetas. So what's the rebound for the first one? Well, theta final is 228.8 plus 0.343, which is m2, times vf2 cos, and our theta 2 that we found, negative 71.0, or 289, whichever one, same thing. So that is pretty much how you set up the first one, right? And then you can pretty much simplify all the left side, and I'm not going to do that because it takes too long. But for when we take the test, simplify the whole left side, and then that'll become one number, and then you can simplify the right side even more, and then it'll just dwindle down to a smaller, expression, pretty much, equation. And then for the y, it's the same exact thing. However, you just change all the coses for sines, because y direction deals with sine. So once you do that, I'm not going to do that because it's literally, I'm going to have to copy the same thing, just sine, 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 sine. But once you do that, you can set those two equations. You have two variables, two equations, and solve for both vf1 and vf2. And that is how to do the first one. And I think if you do this right, it should come out to vf1 equals 4.77 meters per second, and vf2 should come out to 25.4 meters per second. So that is how to do a question like that. Okay, the next question is an explosion. So explosions are honestly easier because there's no rebound and you don't have to think that much for the angles. So pretty much there's a 3 kilogram mass that explodes into 3 fragments. M1 is 1.2 kilograms. That moves 120.0 meters per second. M2, 1.10 kilograms, 110 meters per second. M3, we don't know the mass, we don't know the velocity, we don't know the angle that it explodes at. So those 3 things are the 3 things we are trying to find. So we can really easily find M3 here, right? It's just add these masses, subtract from 3, so 1.2 plus 1.1, 3 minus, and it's 0.7. So that was really simple, 0.70 kilograms. So now we have to find the velocity and the theta, which are 2 variables that we need to know. So first, let's set up our angles. So these are much easier because they're already going out that way. So pretty much to find this angle, we can just do 90, right? Because this is 90 plus 33.2. 90 plus 33.2. We get theta 1 equals 123.2 degrees, and our theta 2 equals, this goes all the way around to 270 plus 26.8, so 270 plus 26.8, which is 296.8 degrees. Okay, so now that we have our thetas, we can set up some equations. So let's start with our x direction. So how does this work? Well, we're going to set up our equation and make it equal to 0. So 0 equals, and then we're going to set up M1 V1, M2 V2, and M3 V3, because we have 3 of them. So M1, what is it? 1.20 times 120.0 times cos, because it's x direction, 123.2 plus 1.10 times 110.0 times cos angle is 296.8 plus our M3, which is 0.70 times, and it's going to be V cos theta, right? and that is all equal to 0. So that is our first equation. And now we can do the y. And this is essentially, like I said, the same thing, but with signs this time. So 0 equals, I'll write it down, 1.2, 120.0, sine 123.2, plus 1.10, 1100, sine 296.8, plus 0.70, v naught, and sine theta. Now we have two equations, two variables, they're both equal to 0. We can equate them, and if we had Desmos, it'd be really easy, system of equations. But you can pretty much simplify this, all of this, and then get, this, and then equate them, and you can solve for v and theta, which I believe our v comes out to 39.0 meters per second, and theta is equal to negative 27.2 degrees. So that is how to do a question like that, an explosion. Okay, the next question is a collision. So when the spring is cut, which we see a spring is connecting these two things, what are the new velocities of each mass? So what can we do? Well, let's set up our things, our m1v1 plus m2v2, right? So first, we know that these are attached by the spring, and they have a 2.55 meters per second. So initially, they're connected. So they have pretty much, we can say, the same mass. So m1v1 plus m2v2 is going to be m1 14.5 plus m2 22.1 times 2.55, because that's m1 plus m2 times v. So that is initial, right? And then that is going to equal our m1v1 plus m2v2, but final. So m1 is 14.5 times v1 final plus m2, 22.1 times v2 final. So that is one equation that we can set up with two variables, and we have two variables, so we need a second equation so we can actually solve for them. Okay, and then our next one is going to pretty much use the energies. So it is going to be our 1/2 mv squared and 1/2 kx squared, all that. So initially, 1/2 kx squared, 1325.154 squared, plus our mass combined, right? So it's going to be 1/2 m, which is 14.5 plus 22.1, v, which is 2.55 squared, right? 1/2 mv squared. And then that is going to equal, once this spring is cut, right, they're going to be two different masses, is going to equal 1/2 m1 14.5 v1 final squared plus 1/2 m2 v2 final squared. Now, what can we do? Well, we can pretty much simplify this once again. We can simplify this all the way down, since there's no variables here. Simplify this side all the way down, and once you do that, you can just do simple substitution, and you should come out with the answer. I'm pretty sure v1 final equals 1.40 meters per second, and v2 final equals 3.30. Really, it doesn't matter if you get it right, because calc error is 0 points off. So as long as you get the setup right, you're golden. So that is how to do a question like that. Okay, the next question is another collision. So this mass is going 17.0 meters per second in the right direction, and this mass is going 3.0 meters per second in the right direction as well, but there is a spring at the back of it, and we have to figure out what is the V at the max compression. So let's think about this. When the spring is max compressed, we know that for a split second, the masses are the same. It's a perfectly inelastic collision is what I'm trying to say. So that means that the masses are together. We can add the masses. So what can we do here? We can use the m1v1 plus m2v2 equals the masses combined times the final velocity. And there we only have one variable, which is quite easy to solve. So what can we do? Let's set it up. So m1 2.00 times 17.0 plus m2 5.00 times 3.00 equals our masses combined, which is 5 plus 2, which equals 7. So 7, I didn't need to do that, 7 times VF. Sorry if that's unclear, 7 times VF. And we can just pretty much do numeric solver. Let's go, we don't have to do that. 2 times 17 plus 15, 49, and then divide by 7, and we get our VF as 7.00 meters per second. And that is our VF. That is how to do a question like that. Okay, so this one's kind of a continuation of this problem here, but now these springs are connected. So originally the V initial for this 2 kilogram mass, it has the same initial velocity, and this one has the same initial velocity as well. So instead, and now we found that the VF, right, is 7.0. So using all this, we are trying to find the delta x. So here, what can we use to find delta x? Well, the spring, which is 1/2 kx squared, right? 1/2 kx squared, and we can try and solve for x here. So what can we do is we can do our kinetic energies and make them equal to each other. So initially it's KE1 plus KE2 is going to equal the KE's combined plus the KE's final combined plus the spring force, which is acting on it. So what can we do? We can do 1/2 m1 2.00 times v squared, which is 17.0 squared, plus 1/2 5.00 times 3.00 squared. And now that is going to equate to 1/2 kx squared, right? K is 4480 times our variable x squared, and that is going to be plus the 1/2, and then masses combined, so 7 v squared. So that's going to be 7, because, right, final velocity is 7 squared. So we can do that. Then we have one variable, numeric solver, and our x comes out to 0.25 meters. So pretty much you have to set up the kinetic energies and equate them to each other for a question like that.